Greetings friends, myself Sushma, studying in MSc Maths first year in NRS Government College in Rohtak, and my roll number is 4710120013. Today I have prepared a topic on field extension. To learn about field extension, we will start from irreducible polynomial. Let us suppose we have a field f and a polynomial f of x that belongs to field f of x, and the polynomial f of x is neither a zero polynomial nor a unit polynomial in f of x, and it is said to be irreducible over f if whenever f is expressed as the product of g of x and h of x of any two polynomials, where these two polynomials h of x and g of x are in f of x, and either g of x or h of x is unit in f of x. Okay. Now irreducible polynomial, a non-zero and non-unit polynomials of f of x that is not irreducible over f is called reducible over f. We will learn this definitions from with an example. Let we have a polynomial f of x is equal to x square minus 2, and its roots of this polynomials are x equal to minus root 2 and x equal to plus root 2. Minus root 2 and root 2 do not belongs to q, that is rational numbers, but it belongs to r, means real numbers. So f of x is irreducible over q, but f of x is reducible over r, which gives us irreducibility of a polynomial depends on the nature of the field. On finding the nature of field, we can find the reducibility of a polynomial. So now the definition of extension of field. Now the extension of a field. A field E is called an extension of field of a field F if F is a subfield of E. It means a field is field extension of all its subfields. Okay. Now next definition is F. Let K and F be any two fields, and we have a monomorphism, that is sigma is K F to K, and f is isomorphic to sigma of f, that is contained in K. Then K sigma is called extension of field F. Since f is isomorphic to f of sigma of f, and sigma of f is a subfield of K, so we can say that f is also subfield of K. So if K and F are two subfields such that f is subfield of K, then K is called extension of F, and it is denoted by K by F. Okay. Now we have some important points about extension of field. Real number is an extension field of rational numbers, and complex numbers is an extension field of real number and also rational numbers. And from here we have learned this. Every field is an extension of itself, means every field is a subfield of improper subfield of the same field, so it will also be an extension of itself, and every field is an extension of each subfield. This we have learned from this definition. Okay, and if E become a vector space over F under the scalar multiplication, thus E must have a basis and dimension over F. Now the degree of an extension. Dimension of K as a vector space over F is called degree of K by F, and it is denoted by dimensions of K over F. Okay, if dimensions of K over F is equal to n, that is less than infinity, so K is called finite extension, and if dimensions K over F is equal to infinity, and then K is called infinite extension. Next is the theorem to be proved, that prove that a finite extension of a finite extension is also a finite extension. For this, let us suppose a finite extension L of k of degree m, and let x1, x2 and xm be the bases of L over k. Now k be any finite extension of f of degree n, and y1, y2 is to yn be any basis of k over f. Here we need to prove that L is finite extension of f, and to prove with finite dimensions. To prove this, we will suppose an element x belongs to L, as x1, x2 and so on xm be the basis of L over k. So we can write x is equal to a1 x1 plus a2 x2 is to am xm, and where all ai's belongs to k, and we can also write this in the summation form. Summation I is to 1 to m ai xi, and now as all ai's belongs to k and y1, y2 is to yn be basis of k over f, then we can also write ai is equal to ai1 y1, ai2 y2 is to ain yn, and which can be also written is in the form summation aij yj, j is to 1 to n, where aij belongs to f. And from this and this, we can write x is equal to double summation I is to 1 to m and j is 1 to n, summation aij yj and xi, where aij belongs to f, where aij belongs to f and yj and xi belongs to n. And here x1 y1, x2 x1 y2 and x1 yn, x2 y1, x2 y2 and x2 y1 and so on xm y1, xm y2 and xm yn spans L over f, and its dimension is m into n. So now we need to prove that L is linearly independent over f. To show that, we will take x is equal to 0, and we have values of x from here and here. Some double summation I is to 1 to m and y is to 1 to n. aij yj xi is equal to summation I is 1 to n, ai xi is equal to 0, and ai belongs to k, and x1, x2 and xm are linear independent over k. So from here we will get ai is equal to 0, where I belongs to 1, 2, 3 is to m, and so on to n. And if ai is equal to 0, then the value of ai equal to aij yj is equal to 0, and aij belongs to f, where and y1, y2 and yn are linearly independent over f. So we have aij is equal to 0 for I 1 to m and j 1 to n, which gives x1 y1, x1 y2, x1 yn, x2 y1, x2 y2 and x2 yn and so on xm y1, xm y2 and xm yn is linearly independent set. Hence dimension over L over f is equal to dimension L over k into dimension k over f is equal to m into n, means the dimension of L over f is equal to mn, which is finite. So finite extension of a finite extension is a finite extension.